Good evening. Ever wonder how a concert pianist achieves such lightning-fast, precise movements? Or a guitarist can shred through solos even without looking? It's all thanks to the incredible engineering of the human hand. Our hand seems to have superpowers, no? It instinctively knows its position even without looking. Ow. But that's really proprioception, which uses specialized sensory receptors. Now, most people think palm lines are for fortune telling. 9. Their palmar flexion creases, vital for flex and grip. But if you insist on knowing how long you'll live, try squeezing a banana. You see, grip and strength is a powerful predictor of how long and how well you live. So don't be one of those limp handshakers. Nobody gonna respect you. Now, the fingers. Did you know only humans and a few primates can do the precision pinch? Thumb to fingertip? And by the way, where are the muscles in your fingers? Ha! They're not there. Fingers contain no muscles. They are moved by tendons in your forearm. Finally, your fingertips. They can feel texture differences as small as 13 nanometers. Truly, the hand is an unparalleled sensory organ that can never be replicated through robotics.
Is that so, Professor? Well, researchers at EPFL's CREATE Lab have developed the ADAPT robotic hand, a bio-inspired device designed for human-like dexterity. Amazingly, it uses just 12 wrist-mounted motors to control 20 joints. Unlike traditional robotic hands that require precise motor control for each joint, ADAPT relies on compliant materials, spring-loaded joints, and a flexible wrist to naturally adapt to various objects without needing sensory feedback or complex programming. Its soft silicon skin and configurable stiffness allow smooth centimeter-scale movements that spontaneously produce complex grips like that needed to pick up small objects like a bolt.
That's impossible! To achieve tactile discrimination down to nanometer levels, engineers would need to develop groundbreaking sensor technology that can accurately detect minute surface variations.
Well, Professor, this robotic hand gets it done by embedding mechanical intelligence into its structure rather than relying on centralized control. That allows the hand to achieve natural motion efficiently.
Oh, I see. That's good. That's very good.
Future enhancements plan to add pressure sensors and AI for adaptive feedback, aiming to make ADAPT a strong candidate for assistive and service robots that interact seamlessly with humans. Well, in order to design such an intricate device as a robotic hand, you need the right parts to do it. So let's check one out in our premiere product highlight, sponsored by Mouser Electronics. The HARTING Cat 6A Ethernet cable is an excellent choice for industrial environments. It features an M12X coded connector on one end and an RJ45 connector on the other, both with 8 positions and male gender. Designed for reliable high-speed data transmission, it measures 2 meters in length and uses 26 AWG wire. The cable's PVC jacket offers durability in industrial environments, making it suitable for demanding networking applications. To learn more, head over to Mouser.com today or click the link below. I'm going to take a wild guess and say it wasn't Chubby Checker who put the twist in twisted pair wiring. So where did it come from? To find out, we present David's Corner.
Thanks, Andy. We've all heard of twisted pair wires in industrial communications, but what exactly is a twisted pair wire and why are they so important? Well, a classic example is the Ethernet cable. These come in category 5, 6, 7, and all kinds of other devices, including like RS-485 and a lot of other standards. But what does it look like inside? Well, if we take a look at the inside of a twisted pair wire, the communication lines are, as we expect, twisted around each other. Now, the main problem with communication lines does not come from how long the wires are by the resistance. It comes from the fact that the capacitance will build up between two conductors, which are wires, side by side. So when the communication signal changes very rapidly, it builds up capacitance, and so we can't get a very long cable. But if we can twist the wire pairs, we actually create inductance in the wire, which cancels out some of the capacitance, and therefore we can get higher data rates at a much longer cable. And that's exactly what we're going for in today's industrial communication, when what we really need is for the wires to be able to be as long as possible, the data to be as high volume as possible, and for the data rates to be as high as possible. Andy, back to you.
Thank you, David. Are you a smart byte or smart bit? Let's find out in our control automation quiz, Smart Bit. Okay, in our Smart Bit quiz, you must match the right answer to its question in less than 3 seconds. The questions are scored using actuator output percentage, and today we'll be testing your knowledge on reversing contactors, plus a tea-serving humanoid robot we named Cha-Cha. At the end, you'll see if you're a smart byte or smart bit. Let's begin with our first question on reversing contactors for 25%. What is the primary function of a reversing contactor in a motor control circuit? Is it A, to protect the motor from overload conditions, or B, to change the direction of motor rotation? And the correct answer is B. A reversing contactor changes a 3-phase motor's rotation by swapping 2 power lines. Overload protection is handled separately by relays. Okay, on to our next question, also worth 25%. Why is an electrical interlock used in reversing contactor circuits? Is it A, to improve current flow between forward and reverse contactors, or B, to prevent both contactors from being energized at the same time? The correct answer is B, to prevent both contactors from being energized at the same time. An electrical interlock prevents both contactors from energizing at once, avoiding phase shorts that could damage the motor or system. Okay, let's move on to our next question about our tea-serving robot, Cha-Cha. This is worth 25%. Cha-Cha is serving tea in a nursing home. When walking across a rug, what robotic system helps maintain Cha-Cha's balance? Is it A, dynamic gate stabilization with feedback from inertial sensors, or B, static posture optimization? The correct answer is A, dynamic gate stabilization with feedback from inertial sensors. Walking on uneven surfaces like rugs require continuous balance correction using IMUs and force sensors to adapt the robot's gait in real time. Let's move on to our final Cha-Cha question, also worth 25%. After serving, Cha-Cha hears the man say, "Dag blast it, I've made a mess." What system enables Cha-Cha to react meaningfully? Is it A, basic keyword detection triggering a vacuum sequence, or B, natural language understanding with situational mapping? And the correct answer is B, natural language understanding with situational mapping. Understanding indirect or emotional language requires NLU and context mapping. The robot must interpret the statement, recognize the spill, and choose a relevant response like offering to help or fetching a towel. Well, how did you do? Are you a smart byte or smart bit? You can have another try at it right now by clicking the link on your screen. Thanks for tuning in, and we'll see you next time.